Investigation of aerodynamic efficiency on NACA 2412 airfoil. Abstract: numerous researches are going on about drag reduction and improving the aerodynamic efficiency of flight vehicles, wind turbines, automotive vehicles, etc., by adopting various methods. One of the basic reasons of drag is the formation of turbulent nature in the rear side of the airfoil and in turn creates pressure drag. The aim of this research paper is to choose best aerodynamically efficient airfoil. Smooth profile of an airfoil is altered by applying certain surface roughness in transition and turbulent boundary layer regions. This alters flow properties and results in reduced drag and increases aerodynamic efficiency. NACA 2412 airfoil in subsonic condition is considered. Airfoil with and without roughness are generated using modeling software. Surface roughness are created for two different shapes at two different positions on the upper surface of the airfoil. The models are then subjected to CFD analysis. Introduction. Aerofoil. An airfoil is the cross-sectional shape of a wing, blade, or sail. An airfoil-shaped body moved through a fluid produces an aerodynamic force. The component of this force perpendicular to the direction of motion called lift. The component parallel to the direction of motion is called drag. Subsonic flight airfoils have a characteristic shape with a rounded leading edge, followed by a sharp with a trailing edge, often with a symmetric curvature of upper and lower surfaces. Foils of similar function designed with water as the working fluid are called aerofoil. The lift on an airfoil is primarily the result of its angle of attack and shape. When oriented at a suitable angle, the airfoil deflects the oncoming air, resulting in a force on the airfoil in the direction opposite and deflection. This force is known as aerodynamic force and can be resolved into two components, lift and drag. Types of NACA series. The NACA aerofoils are airfoil shapes for aircraft wings developed by the National Advisory Committee for Aeronautics, NACA. The shape of the NACA airfoils is described using a series of digits following the word NACA. 1.2.14 digit series. The NACA 4-digit wing sections define the profile by 1. First digit describing maximum camber as percentage of the chord. Second digit describing the distance of maximum camber from the airfoil leading edge in tens of % of the chord. Last two digits describing maximum thickness of the airfoil as % of the chord. The NACA 2412 airfoil has a maximum camber of 2% located 40%, 0.4 chords, from the leading edge with a maximum thickness of 12% of the chord. Impact on roughness factor on aerofoil. Roughness. Surface roughness, often shortened to roughness, is a component of surface texture. It is quantified by the deviations in the direction of the normal vector of a real surface from its ideal form. If these deviations are large, the surface is rough; if they are small, the surface is smooth. In surface metrology, roughness is typically considered to be high-frequency short-wavelength component of a measured surface. However, in practice it is often necessary to know both the amplitude and frequency to ensure that a surface is fit for a purpose. Roughness plays an important role in determining how a real object will interact with its environment. Although a high roughness value is often undesirable, it can be difficult and expensive to control in manufacturing. Roughness can be measured by manual comparison against a surface roughness comparator, but more generally a surface profile measurement is made with a profilometer. 2.2 Rough surface of an aerofoil. An experimental investigation on the effect of surface roughness on a NACA 2412 airfoils is performed. The experiments include measurements for the pressure distribution, drag coefficient and lift coefficient. Two different rough surfaces are analyzed and their data are compared to those over a smooth surface. Measurements are obtained for angle of attack in the range of 0 to 10 degrees. Also, measurements of the velocity and turbulence intensity profiles are collected for the flow around the airfoil at various pre-chosen stations. Design and meshing. 3.1 Design. NACA 2412 aerofoil was designed by using Kamaleshwari software. Kasha V5 version has been used for designing. The chord length of our Naca 2412 Aerofoil is 15 cm. Span wise length of the Aerofoil is 30 cm long. Maximum camber thickness of Aerofoil is 1.74 cm. Then we designed a rough surface on Naca Aerofoil at 2 different positions and 2 different shapes. The first position of roughness is created at 30% from leading edge shown in figure, and second position of roughness is created at 50% from the leading edge shown in figure. Shapes such as rectangular and triangular roughness is created. The airfoil at 0° angle of attack was analyzed by using the above boundary conditions, and pressure distribution of an airfoil is shown in Fig 4.1.1.1, where the values of CL and CD are noted. The design of smooth and rough surface airfoil has been analyzed in Fluent Analyzer. Workbench 14.0 version has been used for analyzing. Rectangular domain is set for 30 mm. The boundary conditions such as inlet, outlet, and wall have been set. Fine meshing is done for accurate results. The velocity is given as 32 m/s. The solution is allowed to run for 200 iterations. Analysis. The airfoil is analyzed for various angle of attack resultant pressure and velocity distributions had shown below. The airfoil at 0° angle of attack was analyzed by using the above boundary conditions, and velocity distribution of an airfoil is shown in Fig 4.1.2.1, where the values of CL and CD are noted. Smooth airfoil at 50 AOA. The airfoil at 5° angle of attack was analyzed by using the above boundary conditions, and pressure distribution of an airfoil is shown in Fig 4.2.1.1, where the values of CL and CD are noted. The CL and CD values are increased at 5° angle of attack. Rough airfoil at 50 AOA. The airfoil with roughness at 50% of chord from leading edge at 5° angle of attack was analyzed by using the above boundary conditions and pressure distribution of an airfoil. Results and discussion. The CL/CDVS angle of attack shows the aerodynamic efficiency of rough is greater than the smooth airfoil is found using computational fluid analysis. The resultant graph was shown below. Conclusion. According to the results of fluent analysis, the addition of surface roughness has proven to be effective in altering the flow properties. With such flow, the resultant lift and drag force are also altered effectively. The triangular surface roughness on the trailing edge is proved to be the most suitable surface modification. Also, there is a reduction in total drag when the roughness is on the upper surface of the trailing edge, i.e., roughness from 50% of chord from leading edge. The graphs are plotted for CL/CDVS angle of attack. Thus, the roughness created on Naca 2412 airfoil shows better aerodynamic efficiency.